This video is on how to create a recursive function that matches a table of values. Specifically, we're going to be talking about when the table has an exponential, a linear, or a quadratic pattern. First, before we do that, let's remind ourselves how to create a table of values that matches a recursive function. So here, our independent variable is our x, and I know that from looking at this right there. Our dependent variable is our f of x, and I know that from looking at here. Okay, so next let's start filling in our values. I know that my first values are when x is equal to 3, my f of x is equal to 2. Okay. Next, to get my next values here, I know for x's that are bigger than 3, so for all of these, which let's just fill in that right now. I know I'm going to use this bottom equation where my f of x is equal to f of x minus 1 plus 5. So a quick little reminder. One way we can think about this, you can think of f of x sort of as your next y value. This f of x minus 1 is one y value before. And then plus 5. So this right here matches this part. Okay, so in order to get this, which is my next y value, I'm going to look at the y value one before, the 2, and I'm going to add 5 to it. So 2 plus 5, 7. This one, 7 plus 5, 12. 12 plus 5, 17, etc. Let's put in this column right here. This is my change column. Two plus 5 gave me the 7. 7 plus 5 gave me the 12, etc. Okay. So few things I want to show here. So one, this x right here matched the variable there. So let's highlight those in the same color. For this, I'm going to pick, let's say, brown. Okay. So that x in our table here matched the x's here. All right, this f of x, like we had said before, let's use yellow. This f of x matched this f of x. Whoa. Okay, apparently I can't highlight that. But that f of x matched this f of x right there. And maybe I can just highlight the f. Nope, okay. Okay, there we go. And finally, our starting values of 2 and 3 were up there, 2 and 3. And this plus 5, or our change column, let's have this be, let's say, red, matched that plus 5. Okay, so this is how you create a table of values from our recursive function. But this video is about how to do the opposite, how to go from a table of values to the recursive function. So let's sort of do that. So if I had this table of values, how would I create a recursive function that matches it? Well, first thing I would do is I know that this right here would match this. So our y for this recursive function is f of x. Okay, I know I'm going to have x's as my dependent variable, both from the variable in here, that x, and by looking over here. So I know I'm going to have x starts with something, and then x bigger than something. Okay. All right. Now let's look at our starting values. I know when x equals 3, my y, or my f of x, is equal to 2. So those values I'm going to use to fill in this right here, 3 and 2. And since it's going 3, then 4, then 5, then 6, then 7, these are increasing in value. So this is going to be when x is greater than 3. I'm going to have some other equation I use. Okay, now, okay, this table should look like this. All right, so looking at this, I could tell this is just the pattern for these values right here is just plus 5, plus 5, plus 5, plus 5. And I can also tell that by looking at my change column over here. So if I was going to have a next value, if I was thinking about how would I find my next y value, the way I would find my next y value is I'll just take the previous y value and I'll be adding 5 to it. So if I know that my next y value is just equal to my y value 1 beforehand plus 5, I know that next y value, that's just sort of like saying f of x, because that's my y, is equal to y value 1 beforehand. The notation for that is f of x minus 1. And I'm always adding plus 5 to it. So I'm always adding this column in order to get the next y value. And that column happens to always be plus 5. So sure. So f of x minus 1 plus 5. There we go. And obviously, this right here was just me using the same example up here. Just want to show you how to go from the function to the table, and then using that same thinking but backwards to go from the table to the function. All right. Let's use a different example now. So let's have this. So how would I go from this table of values to a recursive function? All right, so using that same sort of thinking, first I know that my dependent variable is x's, so x equals something, and then it's going to be x greater than something. I know my independent variable is f of x, so f of x. All right, and I know my beginning values is when x is equal to 4, my y or my f of x is equal to 6. There we go. And since then it goes 5, 6, 7, 8, those are all numbers greater than 4. You obviously don't have to do this highlighting. I am just doing this highlighting to show you how they match. And I noticed that in order to get my next y value, in order to get this 18, I took the previous y value and I multiplied times 3. So for example, this value right here, this next y value would equal my previous y value multiply times 3. So next y is equal to y value 1 before times 3, or that column. Notation is next y value is just your f of x, y value 1 beforehand is f of x minus 1, and I'm always multiplying times 3. There you go. That's what goes here. Your f of x is equal to f of x minus 1 times 3 is how you get all of these over here. All right. Let's do, so those first 3 steps were everything before this line right here is always going to be the same, basically, regardless of whether or not it's linear, quadratic, exponential. Your initial, basically these 4 right there, will just determine every area except for that line. It's just determined right here. Okay. And then determining this ends up being about the same for when it's linear, when it's plus plus plus, the same number each time, or when it's exponential, times times times, the same number each time. Let's look at a quadratic. Ends up being a little bit different. So this right here, let's start off creating our table. And then I'll show you how to go from the table to the quadratic. So our dependent variable here is an n. Our independent variable here is a g of n. That's like your y. Okay. And your n is like your x. My beginning values is when n is equal to 1, my g of n is equal to 5. So 1 and 5. Here we go. All right. And I know for all the rest here, this is just going to be when n is bigger than 1. So what's values are bigger than 1? You have 2, 3, 4, 5. Sure. And just for record, I know I'm counting by ones, like plus 1 here, plus 1 here, plus 1 here, plus 1 here, because this is g of n minus 1. If this had been g of n minus 2, I would count by 2s, like 1, then 3, 5, 7, 9. If this had been n minus 3, then I'd count by 3s, 1, and then this would be 1 plus 3, 4, 7, 10, 13. All right, so let's do this. In order, let me copy for every n value after our first one, we're using this equation right here. Okay. So our next y is equal to our y value 1 before plus this 2n plus 6. 2n plus 6 is just matching this column right here. Okay, so if this was our next y right here, I'd get my previous y, which is 5, plus 2n plus 6. Here our n is 2, so plus 2 times 2 plus 6. Okay, so once again, 5 plus this value here, which turns out to be 2n plus 6, gets me this. 2 times 2 plus 6, that is 10. So 5 plus 10 is 15. So my next y value is 15. All right. Next y value, our next y value here, our next y equal to our previous y, 15, our y value 1 beforehand is 15 now, plus 2 times n plus 6. And our n here is 3, so plus 2 times 3 plus 6. Sure. And once again, this is this column. This is our little red column right here, because 15 plus this will equal this one. Okay. 2 times 3 is 6, plus 6 is 12. 15 plus 12 is 27. So our next y value is 27. Okay. Next y value, you might be seeing a pattern here. Our next y value is our previous y value, 27, plus 2n plus 6. Here our n is 4, so plus 2 times 4 plus 6. Sure, have it look like that. Okay. let's do this. 2 times 4, 8. 8 plus 6, 14. 14 plus 27 is 41. So our next y value is 41. Last one. Next y equal 41 plus 2n plus 6, where n is 5. So plus 2 times 5 plus 6. Okay, 2 times 5 is 10. 10 plus 6, 16. 16 plus 41, 57. There you go. All right, so this was 5, then 15, 27, 41, then 57. Okay, let's create a change column here. Okay, so to go from 5 to 15, that's going to be 10, or 2 times 2 plus 6. Okay, to go from 15 to 27, that's 12 plus 12. You should put a plus here. Sure, plus 12, 10, and this is from here to here, plus 12, which notice that's the same as 2 times 3 plus 6. From here to here is plus 14, which is 2 times 4 plus 6. From here to here, it is plus 14. Notice that is 2 times 10, 2 times 5 plus 6 is plus 16, which is from here to here. Okay, I'm going to copy this one again because I want a record of that. Okay. All right, I just copied it twice. One after I changed it to 10, 12, 14, 16, and this is before I changed it to 10, 12, 14, 16. Okay, so I basically right now just went from a recursive equation to a table of values. Once again though, this video is about going from table of values to recursive equation. Let's see how we do that. Okay, let's say that let's say I don't even have that part yet. Let's say I have this, and you're trying to figure out how to change this to a recursive equation. First thing I need to do is I need to figure out, is this going to be linear, exponential, or quadratic, or something else? Now, is this table, or does this table match an exponential? Well, in order for it to match an exponential, it had to be times the same number each time. Okay? I know 5 times 3 would get me 15. 15 times 3 does not get me 27. 15 times 3 would be 45. And so if this was exponential, this would be 45 here. It's not, so therefore, no, this is not an exponential. Does this table match a linear? Okay, well, in order for it to match a linear, I'm looking at this change column. It'd be plus, plus, plus the same number. Go from here to here, that's plus 10. Here to here, that's plus 12. Here to here, plus 14. Here to here, plus 16. Okay. Now, these are not the same numbers, so therefore this table does not match a linear. But if I created a second change column, or a second difference column, To go from 10 to 12, that's plus 2. To go from here to here, that's plus 2. To go from here to here, that's also plus 2. So does this table match a quadratic? The answer is yes, because our second change column is constant. Sure, let me write these here. No, it's not exponential because not times the same number each time. It's not linear because it's not plus the same number each time. And for this one, that was us looking at the change column. Okay, so we now know this is a quadratic. So let's create a recursive function that matches that quadratic. Like I said before, these for everything except for this point right there, I'm just looking at these four here. So I'll do it in the same order. Our independent variable is n. Our independent variable is g of n, that's like our y. Okay, our beginning values is when n is equal to 1, my g of n, or my y, is basically a 5. Okay, and then looking at these numbers, it goes up by 1 each time, plus 1, plus 1, plus 1 on this side. So I know the rest of my n's are when n is bigger than 1. Okay, now the harder part. This right here is my change column. And if you notice, to get this next y, I took my previous one plus my change column. So this plus that got me 15. This one plus this one gets me 27. This one plus this one gets me 41. This one plus this one gets me 57. So let's talk about an example how to get this. Okay. So in order to get this, this next y, so my next y value was equal to my y value 1 before, 41. And each time I was basically plussing this change column. I was plussing this pardon me. I was plussing that column right there in red. So my next y was always equal to my y1 before plus that change column in red. So this one plus this one, my previous y plus my red column is equal to the 15. To get this 27, I took my previous y plus the red column to get 27. To get this next y value, I'm taking my previous y plussing the red column to get this. Now, unlike our linear, unlike our exponential, that next column is not always the same number. So, therefore, in our equation here, our red column it's not going to just say plus a constant, plus a number, or times a number. It's not going to have just a constant here in red. And that's because our red column here is not a constant. It's changing every time. So what you just need to do is you need to create an equation for that red column. How do we create an equation for this red column? I'm just going to copy that whole table, and let's mess around with this table here. So in order to create this red column, let's look at when we were first creating that red column, when I was going from the recursive function to our table of values. How was this red column created? Okay, well, if you notice, let's take away all the colors here for a second. Okay, now we're just looking at how was this created. Well, if you notice this right here was created using this 2. If you want to be very specific, then this 2 is really that 2. This 3 is that 3. This 4 is that 4. And this 5 is that 5. So this is related to this one, but you notice it's like off by 1 row. Like they're not on the same row. Like here, this green matches the green on the next row. If I wanted them to be on the same row, I would do copy and paste it down 1. And now the greens are on the same row, the reds are on the same row, etc. All right. And as I'm going down this, the only thing that's changing is those colors. It still has a 2 in front, it still has a 6 on the side. All right. So if I wanted to create an equation for this red column, here's what I'm going to do. I'm just going to first pretend this column doesn't exist. Let's just get rid of this because I don't care about that. I'm trying to create an equation for the red column. And I'm going to move it down 1 because this 10 was created using this 2. This 12 was created using this 3, etc. Looking at this, you're going to treat this column right here sort of like your x value. Technically, it's an n, but you're thinking of it right now as an x, and you're going to be thinking about this column as sort of like your y. So if this was an x, this was a y, and none of this rest of this stuff was here, how would you create an equation for this right there? Thinking back to stuff you had learned in previous math courses, you should be able to tell that this here is a line. This is a linear. The equation for this column as an x and this column as your y is a linear. So sort of your y is equal to mx plus b. Okay. So let's create our equation for y equals mx plus b if this was your x's and these were your y's. First, I'm going to find the m here. My m is how much does your y change each time? Well, it changes by plus 2. So your m is 2. M is equal to 2. Okay. Let me actually do that last. Okay, so now we need to find our b. Your b is your y-intercept. When x is equal to 0, how much is your y? So let's insert a row here. We're looking for this value right here. This is your y-intercept right there. Okay. In order to find it, I know this is going down. It's plus 2, plus 2, plus 2 each time. So going up, 16 minus 2 is 14. 14 minus 2 gets me 12. 12 minus this 2 gets me 10. 10 minus this 2 gets me 8. 8 minus the 2 gets me 6. So your y-intercept is 0, 6. Your y-intercept, or your b, is 6. So long story short, your equation for this red column is 2 times x plus b, which is 6. All right. So back to our original. Now that I know that the equation for your red column is, I said 2x plus 6. I'm going to change something slightly there. But this right here, 2x plus 6, is how we created that red column. And here I didn't actually use x's. This uses n's and g of n's. So sure, there's not really an x there. It's an n. Other than that, it's this right here. This matches our red column. So f of x, oops, sorry, it's a g of n. G of n is equal to our previous g of n plus 2n plus 6. There you go. And there we have it. There is that's how we go from a table of values to a recursive function that matches a quadratic. The only real difference between this quadratic and when we were doing it for our exponential or our linear was just this red part. So to summarize how to create this red part, is you take this change column, you move it down one spot, then you find the equation for this red column compared to this column here. This is always going to end up being a linear equation for your red column if the table matches a quadratic. But yeah, you move it down one spot, make the equation for the line that uses this as your sort of your y and this sort of as your x. And there you go. let's have you practice one now. So if we have this table of values right here, I want you to copy that down, try it, hit pause the video, copy that down, try to create the recursive equation that matches this. When you're ready, hit play to see if it matches the correct answer. So pause now. All right. So feel free to skip to the very end if you want to know the final answer. So I'm going to do this though. Looking here, independent variable is n. Dependent variable is g of n. My beginning values, when n is equal to 3, your g of n is equal to -4. And the rest of my n values is bigger than 3. So looking at all the other values, it's going to be when n is bigger than 3. All right. So let's find out does this table match an exponential? Well, I know from 1 to 9, that would be times 9. And I know 9 times 9 would have given me 81, and this is not 81, so no, it's not multiplying by the same number each time, so therefore no, it's not exponential. Okay, from -4 to 1, -4 plus 5 would give me 1. 1 from here to here, this is +8. Here to here, it is +11. Here to here is +14. So it is not linear because it is not adding the same number each time. Let's look at our second change column from 5 to 8, +3. From here to here, +3. From here to here, +3. So yes, it is a quadratic because my second change column is a constant. Okay, since this is a constant, since this is a quadratic, I know this is going to be I'm taking my previous y value and I'm adding this change column. So all I need to do is create the equation for this change column. Cool. I'm going to ignore this column. I'm literally going to delete it, so I can't pay attention to it. And then I'm going to move this one down. And let's create the equation for this change column. Okay, 2, 1, 0. Okay, so you have your y equal mx plus b. Your m value is equal to 3 because it's changing by +3 each time, +3, so your m is 3. Okay, I just need to find this, my y-intercept, which is your b. Okay, so once again, going down, it's +3 each time. So going up, I'm going to go -3. 5 minus 3, negative 2. Oh, I'm so sorry. 5 minus 3 is positive 2. My mistake. 2 minus 3, negative 1. Negative 1 minus 3, negative 4. Negative 4 minus 3 is negative 7. So my y-intercept is negative 7. So your equation is y equals 3x minus 7. Except that here we're actually using an n instead of an x, so I'll change that to an n instead of an x. There you go. There is your equation for your change column. (3n minus 7). Okay.